Radiation. Welcome back, everybody. We are getting into the last topic of this class. It's been quite a marathon. If you remember, we started by looking at energy balances. Then we looked at the very basics of heat transfer mechanisms in which we discussed convection and radiation, among others. Then we got into transient systems in which the temperature was uniform, and that's the case of lumped capacitance. And then we took a look at systems in which there are gradients but are in steady state. And then we looked at systems that have gradients and transients at the same time, and that included the case, for example, of the semi-infinite solid or the spheres and cylinders that were heated from were heated in a transient way. And after looking into those aspects of transient conduction, we looked into convection from the point of view of the fundamentals of convection. And we saw that it had many similarities with conduction, right? And after all, convection is a mixture of conduction and advection. And we looked at convection outside forced convection, in which we impose the velocity of the fluid outside the body, convection inside pipes, tubes, enclosures, and then we looked at a natural convection in which we don't impose an external velocity, but buoyancy, the differences in density of the fluid caused fluid flow and advection. With that, we learned so much about conduction, so much about convection. Then we got into heat exchangers in which we combined all those things together. And now, today, we're going to be discussing the last heat transfer mechanism that we have been using, but without going too deep, which is radiation. So let me tell you something about radiation that is cool. If you have a car, you might cool the engine using a radiator that in reality doesn't radiate anything, but it's all about convection. It's a heat exchanger. But if you are on the moon, you're not going to be using a whole lot of convection because there's no air to do it. So now tell me, how do you cool a vehicle such as this? Sun comes in and heats it up. The motors, electrical motors, way before Tesla, and they generate heat. How do you dissipate that heat? Isn't this interesting? Right? Sure, not all of us are going to the moon, or even in Mars, we would have some amount, a very mild amount of convection. So let's look at how radiation, the last heat transfer mechanism, can operate even when there is no medium, no fluid such as air to help us transfer the heat. So the notes are already uploaded, and let's start seeing some concepts. So radiation is, some aspects is simple, some aspects is complex. The physics of radiation are so deep that the study of radiation is the root of quantum mechanics. So let's start seeing some things. Everything that is hot radiates energy in the form of electromagnetic waves. This energy can be radiated volumetrically. For example, if you have a flame, the fire is hot, and that each element of gas that is in a flame is emitting. That is volumetric emission, right? And in a fire, you feel the heat, right? And the heat by radiation, even, for example, when you see an explosion, you feel the heat by radiation before you get the convective currents that carry heat by convection. So this can be volumetric or can be from a surface. For example, a hot surface is radiating heat from its surface to the outside. This last case is what we have been looking in the class so far, and what we'll keep looking. But to give you an idea, in my research life, when we study welding, this big spark you see in welding, that's a plasma. And that plasma radiates volumetrically. So I need to deal with this type of radiation in the case of a plasma. In this case, in this class, we're going to be dealing with something that is simpler because it's not too simple, but it's much simpler than the volumetric. So radiation is going to be coming out of surfaces between a condensed matter, whether it's solid or liquid, and going through a transparent medium. Can be vacuum or can be, say, typically gases. We have said they are transparent, and we're going to look into more details about that. In these last two classes, this term, I want to discuss some of the fundamentals of radiation, which actually I think is the coolest part because it helps us understand so many things, but it's qualitative. And then on Friday, I want to discuss the quantitative aspects. There are those that are part of your second assignment. So radiation is quite interesting. That is different than conduction in so many aspects that's why radiation is kind of an appendix in this class. We have discussed pretty much everything we wanted. Now radiation comes as like tacked on. Look at this. In conduction, the direction of heat transfer is given by gradients, right? But in radiation, the heat transfer goes from a surface to the other. You don't need gradients. Actually, if the gradients in a transparent medium such as air mean nothing to radiation, and the gradients inside of an opaque body means no radiation. Also, in conduction, let's put this. In conduction, all the heat is the same. Heat is heat, units, joules, or watts. What part of heat don't you understand, right? But in radiation, no, all of a sudden we don't understand because the heat is not the same if it's transferred with a wavelength of 10 microns or 1 micron. The wavelength of this electromagnetic radiation matters a lot. And each different radiation, each different wavelength will have properties. Very literally, each type of, each wavelength is a different color, right? In this schematic we have here, we see wavelength. To give you an idea, the visible light is between 0.4 and 0.7, just shy of 1 micron. And it's not a very broad range, right? 0.4 to 0.7 is less than a factor of 2. If it was sound, this is less than an octave. Our ear can hear like, I think it's like 7 octaves or something like that, maybe more, right? So our ears would cover a much broader range than what we see, right? Interestingly enough, we humans depend so much on vision, but vision is not our most developed sense and it's quite narrow. Now, thermal radiation, right, is beyond what we see. Of course, part of thermal radiation is infrared. Infrared are those long wavelengths, right? And this would correspond to more or less 30 Kelvin, these 100 microns, very long. And this 10 to the minus 1 would be ultraviolet light, right? And this is what we call, and corresponds to more or less 3000 Kelvin. Longer wavelength, we get into microwaves and radio waves, right? Same thing as what we see. It's just like the wavelength is so different that now instead of using eyes or sensors to get this radiation, when it's too long, we use antennas, but it's the same thing. Now, if we go to shorter and shorter wavelengths, we go from visible, we go from the visible to the ultraviolet. And if it is shorter and shorter, we get shorter wavelengths that are X-rays or gamma rays, right? Very short. The relationship between wavelength and frequency, right, is given by the speed of light. Short wavelengths or high frequencies carry very high amounts of energy. So these wavelengths, this type of radiation that is such a short wavelength, including ultraviolet, means they have higher and higher frequency, means have higher and higher, each photon has higher and higher energy. And that's the reason why ultraviolet light can cause skin cancer, because one photon of this short wavelength that is a high frequency carries so much energy that can knock out some parts of the DNA and cause a mutation. Of course, X-rays are even worse, and you don't want to play with gamma rays for sure. So what variables are we going to be looking at now that we said in radiation, not all heat is the same. Some heat has a wavelength, some heat has some other wavelength, and quite not the same. So the two key variables we're gonna be looking at are wavelength, and here we have four, it's a random surface. This is an example, and we're gonna get deeper into this later. For a given surface, at a given temperature, we would have that the amount of radiation that is emitted at each wavelength is different. And some wavelengths are high, some wavelengths are low. The total amount of heat transferred by radiation is the integral of the heat transferred at each wavelength. That's one aspect. The other aspect is the directional distribution, because not only we have different ways of transmitting heat with different wavelengths, but depending on the direction, we're going to have a different effect. It's not the same to emit heat normal to the surface by radiation than to emit the radiation in shallower angles that are close to being parallel to the surface. Things are quite different. So wavelength matter, directional distribution matters. So other concepts that matter about radiation are reflection, absorption, and transmission. So these rho, alpha, and tau are the fractions of energy coming to a surface. And let's talk about a surface that is semi-transparent. For example, a piece of glass, a glass window. Energy comes in, and by energy, I'm talking about radiation, right? Radiation comes in. For example, the light of day. Some of it is reflected. And we know that because in some windows, we actually even pay for having highly reflective window tints, right? Some gets reflected. Some is transmitted, of course, because otherwise we wouldn't see anything. If we reflect all the light that comes in, that's a mirror, right? It doesn't really work that way, right? And when some is transmitted and we see through the window, here we have transmission. And as we know, a window glass is not perfectly transparent, so some amount of it, hopefully very small, gets absorbed. This is a semi-transparent medium. Now, most of the time, and in this class, and actually I think most of the time means essentially 100% of the time, we're going to be dealing with opaque medium in which the transmission is zero. We're going to assume that. And this is true even for glass from the point of view of thermal radiation. So the light that comes in, some will be reflected and some will be absorbed. And nothing is going to be transmitted. And this applies from a piece of coal that is black and absorbs everything to a mirror that is super shiny and reflects everything. Neither of those two are absorbing the light. Neither of those two are transmitting the light. And for that reason, whether it's shiny like a mirror or dark as a piece of coal, we're going to call them opaque. Here we have some words we're going to be using. And of course, you cannot remember them off the bat. I find them difficult to remember because they have all similar names. But I want to tell you what magnitudes we're going to be playing with. One is called the emissive power. And emissive power is at a given temperature, every surface emits energy by radiation, right? Any temperature above 0 Kelvin. And you know that because this is the expression for it. That is sigma T to the fourth, right? And this epsilon is the emissivity, something very, very, that emits most of its light would be epsilon near 1, and something that emits very little of its energy would be a low value of epsilon, such as 0.1. We are used to T to the 4 minus some other T to the 4. In this case, we're talking only about what's coming out. We're going to see later, but on Friday, what happens with the energy that comes in. But you already get the sense that one of the T to the fourth is the energy that goes out, and the other T to the fourth is the energy coming in. Right now, for the emissive power, this is energy going out, and this is the expression. We're also going to say that the emissivity is, in this class, and for all practical purposes, is the same as the absorptivity, such that very dark bodies will be emitting with an emissivity close to 1, and it's pretty much everything you see, except shiny metals that have an absorptivity that is very low, and the emissivity is very low. The metals shine because they reflect the light very much, but not because they emit very much. One thing is emitting because you're hot, the other is reflecting the light. I'm going to show you examples of this. So E, emissive power, is you're hot, you emit. Irradiation is the amount of thermal energy that comes in by radiation. So I'll give you an idea. Beyond all these sigma T to the 4, a laser such as the one we have in the lab, if I aim the laser at a surface, I'm irradiating that surface, right? It's the amount of heat that is of radiation that is coming onto that surface. That's G, irradiation. Radiosity, chances are you never heard this word before, right? And radiosity is kind of a funny concept, but radiosity is all the energy that leaves a surface. And this is important when we deal with gray bodies. We'll see later what those are. So radiosity is everything you're emitting because you're hot, plus everything you're reflecting that something came from elsewhere and you're bouncing off. So that's the same way that irradiation is everything that comes in, radiosity is everything that comes out. And the difference with emissive power is that emissive power is the energy that goes out just because the body is hot. Doesn't matter whether you're reflecting a little or a lot, but radiosity accounts for the reflections. And of course, you have a net radiative flux, that is what comes in minus what goes out. I talked about gray bodies, and the one that really matters is black body. Black body is an idealization, although there are ways in which we can approach a black body quite okay. In work I'm doing recently, we're trying to get a black body to calibrate a thermal camera. And guess what? Getting a black body is really expensive if you want a good one. Why? Because black bodies absorb all the radiation that comes in and let nothing come out. So that's difficult. You can paint things black, And that's a good approximation. Or you can make this cavity in which the radiation would come in and starts bouncing off and is very unlikely to come out. The physics is such, and there is some like a pretty sad proofs in the book. I cannot tell you exactly why, but in this idealization of the black body is that it emits the maximum amount of radiation that anybody can emit. So nothing can emit more radiation than a black body. At a given wavelength, a black body emits so much light and so much radiation, and everything else in real life is going to be a fraction epsilon or fraction alpha, right? Emissivity or absorptivity of that energy of the black body. And the energy of the black body is sigma, the Boltzmann constant, times T to the 4. Another important thing about the black body is that it is a diffuse emitter. A diffuse emitter, as we saw, is exactly the opposite of a mirror. Instead of emitting just in one direction, this emits in all directions with the same intensity, right? This is much the opposite of a laser that emits things in a single direction. In a black body, it emits in all directions or absorbs from all directions with the same intensity. Okay, so that's a black body. And what matters is we're going to be using black bodies a lot, especially to approximate real bodies. So let me tell you about some of the laws of radiation. The book has many. I included this one that I think is interesting, Wien's law. And Wien's law, what tells you, okay, before I tell you about Wien's law, this graph we have here says for a black body, if we have a black body for different wavelengths, for a black body at different wavelengths, what is the emissive power for a black body? What people have seen is something that we can already know intuitively. If the temperature is low, that means if the temperature is low, the emissions are low. And here we see 50 Kelvin, 100 Kelvin, the amount of radiation emitted is low. And as things get hotter and hotter, we know they emit more, because if we put our hand next to the furnace, we feel the heat. And if a piece of iron is very hot, starts glowing red. And if it gets really, really, really hot, it starts glowing white and feels really hot, even if we don't touch it. So we see that with higher temperatures, we emit more. But the most interesting thing is something that we also have seen, but might not have paid attention, and is that the peak of this distribution is at every time shorter and shorter wavelengths. And that's the reason that something that starts to be too hot starts glowing red. It doesn't glow blue, it glows red. And it glows red because that's at low temperatures, that's the longest wavelength. As the temperature increases, the red turns into yellow, and we see that with our eyes. And when it's really, really hot, we don't see it violet. What happens when it's really, really hot is that we see all these wavelengths coming to our eyes, and we see it white. That's why we call it white light, right? And gets hotter and hotter and hotter. When I work with welding, in which the temperatures are not 5,800 Kelvin, are 20,000 Kelvin in the plasma, I see a blinding white light, right? But the peak of the emission is in the ultraviolet. And if you're welding for 1 minute, maybe even less, and you have a piece of skin exposed, you're going to get a tan as if you had spent your whole day at the beach because of all the ultraviolet that is emitted at those really high temperatures. So this is Wien's law that tells you where the peak is. And it's more or less that the wavelength of the maximum is more or less 3000 divided the temperature in Kelvin. Something interesting here. This is quite amazing. Our eyes can see between 0.4 and 0.7 microns, right? This is the band of visible light that is indicated at these wavelengths. This curve is a curve that corresponds to the peak of sensitivity of our eyes. Our eyes are evolutionary tuned to this peak wavelength. You know what that is? It's the surface of the sun. And the surface of the sun is at 5800 Kelvin. That is a peak. It's amazing how we have evolved to have adjusted our eyes to the temperature of the surface of the sun. Isn't that incredible? Now, those of you who are into photography might recognize that sometimes, depending on the light, sometimes the light looks reddish or blue or bluish, right? And if you need to set up the color shade of your photos, the color is measured in temperature. Typically, they have a K. That K stands for Kelvin. Why? Because now this is not exactly true, because fluorescent lights are kind of weird in their spectrum. But essentially, people tell you reddish light, that corresponds to 3500 K. You know what that means? Is using Wien's law is where the peak is, right? Where the peak is. And if we do 3000, as we said, 3000 divided 3500, okay, it gives us 0.857, kind of 0.8 microns. So this is kind of on the reddish side of the spectrum. And 5500 K, that is the whitish or bluish fluorescent light, is the one that is approaching daylight. An incandescent bulb that works very close to a black body is at 2700 Kelvin. Why? Because they have a tungsten filament, and any higher than that, you melt it. Now, the problem is that if you're at 2700 Kelvin, you're in the side of the spectrum in which most of the energy is wasted as infrared, and the little that gets to you, to your eyes, is very reddish. That comes out quite evident when you take a photo that has part of the photo with light coming from outside and other part coming from an incandescent bulb. This is why they look reddish, because they have a low temperature, because otherwise they would melt the tungsten filament. Very interesting, all these aspects of wavelength. I discussed the black body, but let's talk about real surfaces, right? Oh, something else I wanted to tell you that is interesting. Quantum mechanics. Before quantum mechanics existed, people thought that the laws of physics the laws of nature were all understood, except little details here and there. They set out to predict this curve at the beginning of the Industrial Revolution. They wanted to see how much light workers needed to be the most efficient, and what wavelengths would make people most productive. So people were playing a lot with light, not for any deep scientific reason, but for utilitarian reasons. Of course, the physicists were measuring many things. They were getting curves like this. And they would see that as the wavelength was long in the infrared, they would have this behavior. And they could explain this behavior with all the Newtonian physics, assuming like things being like particles. However, those predictions could never account for the curve bending back down as we see in the ultraviolet regime. This is what they call the catastrophe of the ultraviolet. It's like, what's going on that our calculations are so good, we all agree in what is the right thing to do, we get this perfect match on this part of the curve, and then things go crazy because they would get that it kept increasing, not decreasing. Actually, they would get like infinite emitted power. Planck suggested that instead of doing an integral, they did a summation. He couldn't explain why instead of an integral, a summation was better, but said if we just make little chunks, instead of assuming everything is continuous, things work. And the rest is history. All related to this curve and related to radiation. Anyway, real surfaces. This is the spectral emissivity of a black body, right? For each wavelength, we would have different emissivity. This peak here would give us a sense of what temperature we're talking about. And in reality, bodies don't emit this, emit less. Not only they emit less, real bodies, but they also don't emit an exact proportionality. Different wavelengths, they have different emissivity factors. So, but it looks more or less like this. When you do the integral, right, of this curve for the black body, or you do the integral under this area, this is what we would attribute like an overall emissivity to the body. The other aspect to look is that real surfaces don't have the same emissivity. They are, even when they are diffuse emitters, they don't have exactly the same emissivity at all angles. And this is interesting. The normal emissivity is 0, right? This angle is 0. And this is typically what is tabulated, right? Normal emissivity. So a non-conductor such as wood is close to 1. In this class so far, we have been using 0.9 in general, like for glass, 0.9. And for conductors, such as polished metals, is much lower. We have been using 0.1 in this class, give or take, right? But that's not the normal emissivity. What happens is that when we get shallower and shallower angles, a non-conductor such as wood, it starts to emit less, such that if I look at the radiation from emitted at shallow angles from a wood surface, I would get quite little energy. Paradoxically, that's not true for metals. For conductors, for reasons I don't know and I hope to know someday, the emissivity increases at shallow angles. And this has practical consequences. I'm showing you here like thermal imaging of a metallic droplet. This relates to my research in welding, in which people are looking at molten metal falling from the electrode into the weld. So this is quite small. And they're measuring the temperature based on the emissivity. And what I wanted to show you here, this droplet, for example, here, this droplet is more or less at the same temperature, uniform. However, you see that this is yellowish here. Yellow corresponds to higher temperatures, but that's not true that the edges are higher. It's not true that this is some sort of a reflection or shining. You know what it is? That the light being emitted at the edge of the sphere, like as we get to see the horizon of the sphere, is getting this higher emissivity. And because it has a higher emissivity, the thermal camera is fooled into thinking it's higher temperature. But it's not higher temperature. It's just that at shallow angles in a metal, we see this higher emissivity. We have a $150,000 thermal camera in our lab, right? And it's fooled just like anybody else with these shallow angles. So what we have something so expensive, we need to be equally smart to analyze what we see and not to be fooled by details like this change in color that does not necessarily mean a change in temperature. So spectral emissivity. So the spectral emissivity is for a real body, how much radiation is emitted at each wavelength. So we get to see that for different wavelengths, things like, for example, aluminum oxide are low and then they are high, they can be low again. Things like stainless steel or tungsten, except the aluminum in the silicon carbide, most of them kind of tend to go down with wavelength. So longer wavelengths, less emissivity. This is more or less independent of temperature. So this emissivity, that is the relationship between how much you emit in reality at that wavelength and how much a black body would emit at wavelength, is more or less independent of what temperature we're talking about, more or less. Now, this temperature dependence, right, is the temperature of, now not the spectral emissivity. This is not emissivity for a given wavelength, but the integral of the curve. So this curve we saw before was for each wavelength, right? You see the horizontal axis is wavelength. And this curve we see now is the integral of all these curves. So we don't worry about wavelengths anymore. And what do we see? That at higher temperatures, right, things like stainless steel or tungsten, at higher temperatures, the emphasis is on the shorter wavelengths, as we have seen. And shorter wavelengths tended to have a higher emissivity. That's why stainless steel or tungsten, we see it go up. Conversely, if you remember this aluminum oxide, at higher, longer wavelengths, that means lower temperatures, it used to be high. So we see in aluminum oxide the opposite behavior. All this can be explained, but we need to understand what is a spectral distribution, what is an overall distribution, and always keeping in mind that now heat is not the same as it used to be. Every time we talk about heat, we need to say heat at what wavelength. And here we have emissivity coefficients for a bunch of different materials. And the reason I want to share this with you is because in this class, we've been using 0.9 for pretty much everything, right? Except for polished metals that we use 0.1. Here you get to see a little bit more nuanced differentiation between different emitting surfaces. I have books on this. Just like everything we have discussed in this class, somebody made a living out of this. Somebody studied this for a whole career. And we are just say 0.1 for shiny metals, 0.9 for everything else. That was a gross oversimplification. I'm not going to worry about that. But I'm going to show, but I'm showing you here that actually is not exactly 0.9 and 0.1. There is a whole range of grays, and there are places where to go find them, the actual values. I took this photo during a project for the Apega Science Olympics with a elementary school team. And this is really cool. By the way, the kids got a gold medal for this. And this is when we were testing their experiment. And I had a kettle here. And this kettle is very interesting because the kettle was pretty much all at the same temperature. We had the hot water in here. And this wall is made out of shiny metal. And the cap is made out of black plastic. Everything was more or less at the same temperature. Actually, the metal was quite a bit hotter. However, let's look at the thermal imaging. In the thermal imaging here, we see as if the metal was colder and as if the lid is glowing hot. what's going on? The same story that we discussed before. The camera measures radiation and believes its temperature. However, these two materials have different behaviors. The metal has an absorptivity that is very low, like 0.1, right? And emits very little radiation. And the camera thought the metal was cold. The lid is black plastic and emits with emissivity more or less 0.9. And the camera is believing it's super hot because it's getting lots of radiation. Not true, right? We see this image that is from a thermal camera. This is not ours. This is a cheap camera, but our camera would look just the same. And you could be fooled, but not you guys, because you're taking this class and you're starting to see how to interpret these images with your understanding of emissivity of different bodies. Two interesting things here. Here, this is me pouring water, and the water looks like as if it was molten steel, right? The water, as we have said, is, for our purposes of the class, opaque for radiation. And that's what you get to see here. The surface of the stream is emitting radiation. And the other interesting thing here, this rectangle you see, these are my glasses. But my glasses are transparent. But as we have discussed, glass is not transparent to thermal radiation. It's transparent to visible light. But thermal radiation is quite opaque. And you get to see here. Let's talk about reflectivity. Reflectivity can be of two types. One is diffuse reflectivity, right? That is, of course, this is not like a black body, because black bodies don't reflect anything. They absorb everything. But most real surfaces are diffuse. Light comes in, and then it gets scattered in many directions. That's what photographers bank on when they put different surfaces to reflect light, but they don't put mirrors. They just put a white surface or a black surface, things that on which well, not the black surface, but the white surface, the light comes in and is distributed. Same like professional photographers typically aim the flash at the ceiling, not at your face. If they aim the flash at your face, you appear like to be like in front of a fire. But if they aim the flash at the surface, at the ceiling, this diffuse reflection fills the room with light. Now, there's another type of reflection, which is that of a mirror. And that is what is called specular reflection, right? Light comes in, light goes out with the same angle it came in. Let's talk about reflectivity of real surfaces. So these are diffuse reflectors, and this is spectral reflectivity. And what do we see? We see interesting things. These are different wavelengths, right? And visible light is, we said, is between 0.4 and 0.7. It's around here. Look at this. Reflectivity of snow is high. And that's why we need sunglasses when we go skiing. Reflectivity of white paint, very high, right? All things that we know. A white room is brighter. Now, this is in the visible range of visible light that corresponds to the temperature of the surface of the sun. Now, we seldom have things that hot. We can have things hot at 100 degrees, 200 degrees, things like those. And in that case, we're talking about wavelengths that are of this order of a few microns, right? And what do we see? We see that white paint, you see, white paint, from the point of view of thermal radiation, guess what? It's pretty much a black body, doesn't reflect much, sucks up all the heat. Even better, look at snow. Snow at 1.5 microns becomes black. Isn't this interesting? Snow, the bright white snow that can blind us when it's reflecting the light of the sun. But if I have a fire, the heat of the fire gets absorbed by the snow, and that heat at lower temperatures doesn't get reflected. Very interesting. Black paint has a very low reflectivity all across the wavelength. Black paint is always black. But white paint, depending on the wavelength we're talking about, white paint is quite black. Snow is quite black from the point of view of thermal radiation. I think it's pretty cool. Let's talk about transmissivity. And this is another cool thing that has lots of technological implications. Something very transparent would have a transmissivity of 1. For example, fused quartz, right? And here we have between 0.4 and 0.7. This is our the range of visible radiation. And what do we see? Yeah, fused quartz glass, very transparent. However, at high wavelengths, a long wavelength, this becomes, the fused quartz becomes a piece of wood, becomes super absorbent. It doesn't transmit anything, becomes very opaque. And the same with other polymers. This is interesting. In my world of welding, sometimes we use lasers. We have like an amazing laser in our lab. And there has been a big revolution because the old school lasers, the CO2 lasers, they're very powerful, but their wavelength is at 10 microns. Now, the laser light is a light. You like to use lenses to focus this light at 10 microns. There's no such thing, because just like fused quartz at 10 microns is a piece of wood. The light doesn't get through it. And there's no other glass. When you have this type of lasers at 10 microns, there's no optical system, no transparent optical system. They can only work with mirrors. So CO2 lasers look quite Egyptian, in which the laser beam is bouncing all around through mirrors, and the focusing is all done through mirrors. And that has a problem, because if you want to you have your laser in one place and you put the light in the other place, you have to start bouncing the light all over the place. And between summer and winter, sometimes the ground gives way just a tiny bit. Your laser is all out of whack. That has happened to companies here. New laser technologies work that are based on semiconductors work at about 1.5 microns. And see the world of difference, that instead of a laser at 10 microns, you work with a laser at 1.5 micron. And all of a sudden, you can use glass. So you can use optic fibers, you can do all kinds of things that you couldn't do before. Now, the laser, instead of being an Egyptian contraption of mirrors and incredible complexity, now you have like an optic fiber, and you do whatever you want with it. Super interesting. And all this is based on these properties of transmitting thermal radiation depending on the wavelength. So let's talk about global warming a little bit. Here, we have the same curves. We know this is the spectrum. And this is the energy coming in from the sun. And of course, the sun is not a black body, so we get to see some deviations from a black body. And also, the water vapor that is in the atmosphere absorbs some of the sun's energy. So you see these kind of things coming down, they correspond to these peaks you see here. The absorptivity of water vapor, is what causes this dance in the energy of the sun coming in. Now, let's talk about greenhouse effect. This energy came in, it warms the earth, and the energy is going to come out. But now it's not the same energy anymore. You'd say a joule is a joule. Yeah, but energy from the sun came as a joule below 1 micron, and now it wants to go at temperatures that are, I don't know, 20 degrees C. We're talking about things that are of the order of 10 microns, right? And at 10 microns, we have a problem because water vapor is not transparent to radiation at that temperature, at that wavelength. So here you have the absorptivity of water vapor, and it's killing all these that should have come out at room temperature. You see water vapor here. How about CO2? So water vapor is the main absorbent, but CO2 also kills part of the wavelength. So this is what is trapping some of the heat that comes into the earth, right? And when I mentioned to you that radiation at night can be, you're radiating to the outer space at 0 Kelvin, I made clear on a dry place. So some places on Earth are very dry and you radiate to the outer space at 0 Kelvin. But some places on Earth are pretty humid and moist in the atmosphere. And you radiate actually to the atmosphere that is absorbed by the water vapor that is in the atmosphere at the atmospheric temperature. All right, let's stop here, and we are going to resume on Friday. Thanks, everybody. Friday will be our last day. Bye-bye.